Greetings. Welcome to Electronic Circuits 1, lecture number 7. I am Razavi, and today we will talk about diode circuits and applications. We saw in the previous lectures that diodes are interesting devices because they distinguish between positive and negative voltages. So today we want to see how these diodes come into practice and also how we go about solving circuits that include diodes in them. Now, before we jump into that, let's just take a brief look at what we covered in the last lecture, namely the different models that we have for diodes. We saw that diodes fundamentally follow an exponential relationship between their current and their voltage. But using this exponential equation is often cumbersome in manual analysis of circuits. So we thought perhaps we can make a simpler model, which we call the constant voltage model. And in that model, we have zero current up to a certain forward bias voltage, VD on, and then suddenly the current can increase arbitrarily. So we said that with the constant voltage model, our electrical representation of the diode consists of two different possibilities. If the diode is off, it has no current, then it's just an open circuit. So it's like a switch that is turned off. On the other hand, if the diode is on, and it's on at a voltage of VD on, then it is like a switch that is turned on, but in series with a voltage source of value VD on. Without that voltage source, this vertical line would be at zero, not at VD on, and that's why we need that voltage source in series with the switch. So anytime we have a diode in a circuit and we are thinking of using a constant voltage model and we know that the diode has turned on, then we can replace it by a short circuit and a battery, or just a battery because the short circuit doesn't really play any role. All right, now there exists an even simpler model for the diode, one that passes, so to speak, positive voltages and blocks negative voltages, and that would be as simple as what we see down here. So in this case, the diode is off if the voltage across it is negative, and as soon as the voltage wants to become positive, it turns on and it becomes a short circuit. So that's even a coarser approximation of this exponential behavior. All right, today we'll just summarize these concepts and look at them a little more closely, and then we talk about an application of diodes before jumping into some diode circuit analysis and practice. All right, so we say that I can use this pen. The diode models that we have so far consist of the exponential model, the constant voltage model, and the ideal model. These models share some properties. They have some properties in common. So what are those properties? All right, so all three models are non-linear, meaning that they are quite different from what Ohm's law predicts. As you can see, the exponential is non-linear, the constant voltage model is non-linear, and the ideal model is non-linear. Okay. All three models distinguish between positive and negative voltages. As you can see here, for the exponential model, if we have a negative voltage, we have no current. If we have a positive voltage, we have some current. For the constant voltage model, the distinction is really around this voltage. So the voltage has to be positive enough to make that distinction. for the diode to be on or off. And for the ideal model, we have a precise distinction between negative voltages and positive voltages. The distinction that we make between positive and negative voltages is important in many applications, one of which we see today, and that is called rectification. So this is called rectification. Rectification means we treat the positive voltages differently from the negative voltages. Usually it means we keep the positive voltages and we throw away the negative voltages. All right. So the other property that we can see is that the constant, sorry, maybe I should do this in order. So the ideal model passes, again I put this in quotation marks because that's a loose way of saying things, passes positive voltages the constant voltage model passes voltages greater than VD on. As you can see here, once the voltage wants to exceed this, we let it go through the switch, go through the circuit. And finally, the exponential model passes voltages significantly, so that's the key word here, substantially, for if VD is greater than about 700 to 800 millivolts. And again, this goes back to our previous studies where we saw for typical current levels in a forward bias condition, the voltage that we would have across a PN junction or a diode would be about 700 to 800 millivolts. So even though the exponential model has some current around here, we don't worry about it too much. It's not a whole lot of current in most applications. So we say that, yes, around 700, 800 millivolts, the exponential model also begins to have significant current conduction. The only distinction between these two models is that we do remember this is an exponential, whereas here we approximate it by a vertical line. Okay, so these are some attributes of these three models. And as I said before, we use the ideal model maybe 10% of the time, the constant voltage model maybe 80% of the time, and the exponential model maybe another 10% of the time. So the constant voltage model is the most common and popular model for analyzing diode circuits. All right, so that's a quick summary of what we have here. And again, I would like to draw the symbol for the diode so that we remember what it looks like. The arrow on this side represents the P side of the junction. It's called the anode. And the vertical line represents the N side, and it's called the cathode. So the current wants to flow in the forward bias region from this side to this side. That's the only significant current that a diode can carry. Very well. Let's now talk about one application of diodes in practice, which is very interesting, and you can find it everywhere. And that application is as follows. So we'll talk about one application example. and that is the chargers or adapters that you have for charging the battery in your mobile devices, in your cell phone, in your laptop, etc. So here's what we have. Here's a charger that we use for a laptop. On this side, we plug it into the outlet in the wall. We receive 110 volts in US, 220 volts in other countries, 60 hertz in US, 50 hertz in other countries. So that's what we receive, an AC voltage. And on this side, we deliver to the laptop a DC voltage, a constant voltage of about 19-20 volts. That's the standard for most laptops. For cell phones, it would be smaller. It would be maybe 3 volts, 3.6 volts. So the question is, what's inside here? How do we go from 110 volts AC or 220 volts AC to, for example, 20 volts DC? So that's something that we are curious about in this charger. So let's break it down step by step and see if we were to think about this fundamentally, what operations would be necessary, what circuit functions would be necessary to go from that large AC voltage that comes out of the wall to 3 volts for the cell phone or 20 volts for the laptop. Okay, well, so here's our charger. And on this side, it receives an AC voltage. We say, for example, 110 volts and 60 hertz, meaning 60 cycles per second. It's a large voltage, and of course that's not something we want to touch because it can be quite damaging. All right, on this side, when we generate a voltage between these two terminals, it's a DC value. So this is as a function of time here, and here as a function of time, the voltage that we measure looks like this. And this value, in the case of the laptop, is 20 volts. In the case of a cell phone, is 3 or 4 volts. All right, so what is in this black box? How do we go from this type of waveform to this DC level? And that becomes a very interesting study. Okay, all right, well first, this voltage is very large. By the way, when we say 110 volts, it doesn't mean that this peak to peak or this peak is 110 volts. So in fact, the peak value from here to here is 110 volts times square root of 2, in case you are curious. So this peak to peak voltage is 2 times 110 times square root of 2. So it's a very large voltage swing. We need to reduce this to something that eventually can be translated to a DC of 20 volts. So how do we reduce a large voltage swing to a small voltage swing before we convert it to DC? Well, you can use a resistive divider that you have seen in basic circuit theory. If you remember, a resistive divider looks like this, and it attenuates whatever we give to this side. So if we give it a large sinusoid here, then on this side we'll have a small sinusoid. You can do that. But we don't use this inside the charger. Why? Well, the problem is that when you apply such a large voltage to this resistive divider, we burn a lot of power in these resistors. So this charger will heat up dramatically, and that's a waste of energy. So we don't want to do that. We want to look for something that is more efficient in reducing the swing without dissipating energy. So we should look for some other element besides the resistor. Some element that at least nominally does not have power dissipation. So what elements do we know that don't have power dissipation? Well, in the ideal case, a capacitor, an inductor, and a transformer don't have a power dissipation. These are all reactive components. So perhaps what we should do is try to build this attenuator out of those components. And it turns out that the best solution is a transformer. So we take a transformer. So in step number 1, we use a transformer to reduce the voltage. So we start from a large swing here, and then we produce something smaller here. So let's say if this is 110 volts, then this might be 15 volts or 20 volts or something in that range. So let me write 20 volts just to avoid any confusion. So we'll make this 20 volts. Okay, so at least we reduce the swing to something manageable, something that at least does not electrocute us when we touch it. All right, but we still have some way to go, because that swing, that signal or that voltage is AC. We need to go to DC. Somehow we have to go from that waveform to this type of waveform. So how do we do that? That's an interesting situation. Okay, well, in the next step, this is what we do. We take this waveform. Let me draw some more cycles of it. So 20 volts and 60 hertz or 50 hertz, depending on which country you are in. And we give it to something, some black box. And what comes out of this black box has only positive half cycles. So we get rid of these negative half cycles. So now what we have on this side has only positive half cycles. Isn't that interesting? Is this a linear operation or a nonlinear operation? What's inside that black box? Well, it's a nonlinear operation, because if we perform any linear operation on a sinusoid, we should still get a sinusoid. Obviously, this is not a sinusoid. It's not a pure sinusoid. So that box is a nonlinear box. And we have to see what could be inside that box. All right, so let's say for now that we have done this, and we got this type of waveform. Is this waveform close to what we want? Well, somewhat. If you look at that waveform, what can we say about the average value of that waveform? The average value is computed by integrating the waveform, meaning finding the area under the waveform in one period, and then dividing it by the period. So let's look at one period from here to here and find the area. This is the area of half cycle, and then 0. So the total area under the one cycle is non-zero. So we can say that the average value of this waveform is non-zero. And that is different from what we had here. For these sinusoids, if you remember from your signals and systems, the average is 0, because if we integrate, find this area and find this area, they cancel each other, and we end up with 0. So when we went through this black box, through this nonlinear operation, magically we created a non-zero average at this output. All right? So that's close to what we want. We want some sort of constant value. Average means DC. So we want some DC. The problem is that in addition to what we want, we also have some other stuff here. In fact, if you remember your Fourier series, we know from Fourier that if we have a periodic waveform, then we can decompose it into a bunch of sines and cosines at harmonic frequencies. So what we have here consists of a DC quantity, the average value of this waveform, plus a frequency at 60 hertz in the US, 120 hertz, 180 hertz, etc. So how do we get rid of all these other frequencies that we don't want? Well, we can use a filter. So in the third step, We take that waveform and we give it to a filter. So this is a low pass filter. And what we obtain at the output is approximately constant and has a little bit of a variation on it, but that is the DC value of this waveform. Remember what the low-pass filter does. A low-pass filter has a frequency response like this. So if the corner frequency is low enough, it will cut off all the high-frequency components here, 60 hertz, 120 hertz, 180 hertz. The only thing that it lets go through is DC, and that DC will be of this form. So we see that if we have a transformer and a black box and a low-pass filter, we can construct a very simple rudimentary charger, which takes a 110 volt or 220 volt line voltage and gives us a DC of 20 volts or 5 volts or something like that. The only mystery at this point is what's inside this black box. Okay, so what is inside that black box? That black box says, I pass positive voltages and I block negative voltages. And of course we know what that is. That is a diode. Ideally, an ideal diode, right? Because that's what the ideal diode did. It passes positive voltages and stops negative voltages. We don't have an ideal diode in practice, but we can approximate it by a real diode, maybe with a constant voltage model. So if the voltage is positive enough, it passes through. If it's negative, it doesn't pass through. So as we go from here to here, conceptually what we're thinking is we need a diode on this in the circuit so that when the voltage becomes positive, it passes through the diode and we get it at the output. When the voltage becomes negative, it doesn't go through the diode, we don't get it at the output. So we have rectification. So when we go from here to here, we say we have rectified the waveform. So this process is called rectification. So that's interesting. We see that this is what goes on inside this charger, right? So we start out with 110 volts or 220 volts. We have a transformer that steps it down, reduces the swing to something manageable. Then we have some sort of rectification circuit consisting of one diode or maybe more. As we will see, actually we might use 4. And then we go through some filter. A filter may consist of resistors and capacitors. It turns out that we just need a capacitor or 2, and we use a capacitor, and then we get a DC. Now, what I'm explaining here is not exactly what goes on inside this. It's a little more complicated, but at least for our purposes here, that will suffice. Very well. This is an interesting application of diodes in real life. Now, we have seen these concepts, and we are ready to go over some circuit examples. My objective today is to make us more and more comfortable with circuits that have diodes in them. You can see that these circuits can be quite nonlinear, and analyzing them is not as straightforward as what we have seen in basic circuit theory courses. Ohm's law applies when we have a linear resistor, but otherwise we have to be very careful. So our objective is try to reduce a given circuit to different regions of operation, and in each one of them try to have a circuit that's linear and manageable. But we have to be careful about how we go from one region of operation to the other region. So we will go through a bunch of examples of diode circuits, and first, for simplicity, we assume an ideal diode model, just like that. This is the simplest model we can have for a diode. Pass positive voltages, don't pass negative voltages. And when we say pass positive voltages, it means that as soon as the voltage wants to become positive, it becomes a short circuit. It's just a switch, if you remember. So right here, we just have a switch that is on. It's a short circuit. Whereas on the other side, we have a switch that's off. So that's all there is to it. An open circuit, a short circuit. That's all a diode does, an ideal diode does. So we go through a couple of examples like that. Then we say, okay, let's make it a little more realistic. And we go through examples using the constant voltage model. That's a little more complicated because that transition doesn't happen at 0. It happens at VD on, 700 to 800 millivolts. But these will gradually acclimate us to the analysis of diode circuits. Okay, so we're going to start with some examples using only the ideal diode model. So here's an example of the ideal diode model. Okay, so in this example, we would like to plot part A. We would like to plot the current through this network as a function of Vx as Vx goes from minus infinity to plus infinity. All right, so here's how it goes. Ix, Vx. All right, so we start with Vx at minus infinity, a very negative voltage. We have to make an educated guess as to what state the diode is in. Is it on or is it off? Well, if this voltage is negative with respect to here, let's say minus 10 volts, then we have minus 10 volts here, which means we probably have to have a negative voltage here. And if there's a negative voltage on the anode of the diode with respect to its cathode, then the diode is off. If the diode is off, there's no current here. If there's no current, it's an open circuit. So I can say that so long as Vx is negative, the diode is off, there's no current, Ix is 0. Now, to keep things organized, what I will do is in every region of operation, I will redraw the circuit to make sure I can keep track of all the details that are happening around the circuit. So for Vx equals, for a negative Vx, this is the circuit. We have Vx, we have resistor R1, and the diode is not there. It's an open circuit. So here's a switch, just to remind us that there is something there except that it's open. All right, so no current can flow here in this loop. The loop is broken. Ix is 0. So Ix is 0. So in this region of operation, that is the equivalent circuit that we have. All right, in the next step, we let Vx cross 0 and become positive. If Vx is positive, so let's say this has gone to plus 2 volts or plus 1 volt, we sort of expect that this would be positive with respect to here, so the diode has turned on. If the diode has turned on, then it can be replaced by a short circuit if it's an ideal model. So I will draw the circuit again in this region of operation to make sure that I remember what is going on. So here's a switch to represent a short circuit, and here's our input voltage Vx. And the current Ix is flowing this way. How much is Ix? Well, all we have is a voltage and a resistor. This is a short circuit. It's a piece of wire, right? So we have Vx over R1 is equal to Ix. So Ix in this region is Vx over R1, which means the slope is just 1 over R1. And that's not that unfamiliar. We saw an example last time that was quite similar to this example. Very good. So we managed to find the current as a function of voltage as the voltage goes from minus infinity to plus infinity. And of course, it's a rectifying circuit because it distinguishes between negative voltages and positive voltages. All right, now before we go to part B of this example, I want to raise an important point in analyzing diode circuits. Let's say that we are given a circuit, and let's say we have one diode or more. We're just looking at one diode. And we are wondering if, for a given amount of this Vx, the diode is on or off. We have to make that determination at this point in order to replace the diode with an open circuit or a short circuit. It's not arbitrary. But if the situation is complex, it may not be obvious at that point whether the diode is on or off. So if I say Vx is minus 2 volts, am I sure that the diode is off? How do I know that? Maybe the analysis would be too complicated without carrying out the calculation all the way to the end. So what approach should I take to make sure that whatever I do eventually is correct and consistent? Okay, well, fortunately, a diode has only two possibilities, on or off, whether it's ideal or whether it's constant voltage, right? Okay, so we have only two possibilities for a given diode. We will try to make an educated guess, but even if our guess is wrong, we have to see at the end whether the results that we obtain are agreeable to the original assumption that we made. So, for example, we assume the diode is on, we calculate everything, and we obtain the currents, and we check. If the currents make sense, then sure, the assumption was correct. Or if we don't know, for example, by accident, we assume the diode is off. No problem. We carry out the calculations, go out all the way to the end, and then see what we get. If the result agrees with the assumption is correct. If it contradicts, then the assumption is incorrect. So here, let me change the color of my pen and show you what happens if we make the wrong assumption. Okay, so let's start with the wrong assumption. Let's assume that I just didn't know what was going on, and I decided to say that D1 is off for Vx negative. Okay, I just didn't know, so I said, I think D1 is off. All right, no problem. So if D1 is off, D1 is on for negative Vx. D1 is on for... So I wasn't quite familiar with the circuit, so when I saw, I said, yeah, I think when Vx is, for example, minus 1 volt, this diode is on. I was confused. No problem. We'll proceed with our calculations and see if the final result for this region, it makes sense, if it agrees with the assumption. If it does, good. If not, then the assumption is wrong. Let's proceed. If D1 is on for Vx less than 0, if D1 is on, it has to be replaced by what? It has to be replaced by a short circuit. That is non-negotiable, right? If it's on, it's a short circuit. It doesn't matter where it is. Okay, so let's do that. Let's construct a circuit. Vx, R1, and because I am saying D1 is on, I will replace it by a short circuit. It's an ideal diode model. No problem. Let's find Ix. How much is Ix? Ix is equal to Vx over R1. Like before, right? So Ix is flowing this way. That is the direction of Ix that we have assumed from the beginning. And we know that Ix is equal to Vx over R1. So far, so good. Nothing seems out of order yet. All right, now let's examine the results carefully. We said Vx is negative. Vx is negative. Therefore, Ix is negative. if Ix is negative, which way is it actually flowing? If Ix is negative, it means that it's flowing this way, right? Because this arrow was the arrow we associated with Ix when Ix is positive. So if Ix is actually negative, it has to be flowing this way. So if Ix is negative and it's flowing this way, it means that it's flowing upward through the diode. So if I draw the diode as a shadow out here so that you remember where it was and how it was, what we have concluded from this assumption is that a current is flowing through the diode of this amount, but the current is flowing from the cathode to the anode. The current is flowing upward. And we know that that is incorrect. We know that if a diode is on, it must carry a current from the P side to the N side. It cannot carry a current from the N side to the P side. So because Vx is negative, and because Ix is negative, and because it flows upward through the diode, this result is incorrect. It doesn't make sense. If it doesn't make sense, it's because the original assumption was wrong. This is a critical point, because once the circuit has a few more diodes, it can be quite complex, and we are sitting biting our nails trying to decide whether this diode should be on or should be off, etc. No problem. You just assume whatever you want, you proceed, but then you have to interpret the final results very carefully and see if they are sensible, if they agree with the original assumption. Very well. Let's now continue to part B of this problem. In part B, what I will do is add a resistor to this network. So let me change the color of my pen to maybe this one here. So in part B, we would like to analyze the following circuit. We have a resistor, a diode, another resistor, and the same situation as before. So we have Vx, R1, R2, and the diode. And we are still interested in the current Ix. So that's the only difference between the circuit in part B and the circuit in part A. We came along and added a resistor here. Why did we do that? Well, this is just because we want to make the circuit more interesting. We want to create challenges for ourselves to become more and more comfortable with analyzing more complex circuits. All right, so in this case, what do we do? Well, just like before, we start out by assuming that Vx is very negative and see what happens. And then gradually increase Vx towards 0 and then towards positive values. All right, so if Vx is very negative, what do we expect? Well, again, we expect that this voltage would be probably negative with respect to here, which means this diode will be off. If the diode is off, how much current do we have in Ix? Well, it's not 0 anymore, right? Because if the diode is off, the voltage source Vx is connected to the series combination of R1 and R2. So if Vx is negative, the current is given by Vx over R1 plus R2. So we say if Vx is negative, then Ix is equal to Vx over R1 plus R2. Because the diode is off. The diode is an open circuit, it's gone, we don't worry about it. So that's an interesting distinction between this circuit and the previous circuit. In the previous circuit, when the diode was off, we had no current, but now we do have a current. All right, so can I plot this on the same axes? Yes. We see that because now we have R1 plus R2 in the denominator, the slope of this line is smaller than the slope of that line. That is 1 over R1. This is 1 over R1 plus R2. So for the new circuit, this is what it would look like. Sorry, let me exaggerate that so that we see it better. So we have something like this, a straight line here with a slope of 1 over R1 plus R2, as long as Vx is negative. All right, now what happens when Vx is positive? Well, when Vx goes positive, we're trying to create a positive voltage here, and as soon as we try to do that, the diode turns on and becomes a short circuit. So we are right here for the diode. Diode becomes a short circuit. If the diode is a short circuit in parallel with R2 what gives us what? Well, we have zero resistance here in parallel with a finite resistance. The net result is still zero resistance. The zero resistance dominates. So if Vx is greater than 0, then the circuit reduces to just R1 and the short circuit, like before, R1 and the short circuit. So we see that Vix is just equal to Vx over R1. So interestingly, for a positive Vx, this circuit and this circuit have the same current. So that current will just coincide with this one. I'll just draw it next to this one here. Okay, so these two coincide. So we see that by adding a little resistor in the circuit, we did create some changes in the behavior of the circuit. Not over here, but over here. So that's an interesting twist to that example. Okay, let's go to the next page. I would like to talk about two different types of characteristics in electronic circuits that we need to keep in mind. So we have types of characteristics. All right, so in electronic circuits, we are often concerned with two types of characteristics. And it's good to understand exactly what they mean, and then, of course, try to derive these characteristics for different types of circuits or devices. So the first type is what we call IV characteristics. And all this means is that I have some sort of box, some sort of device, or a complex circuit or something. I apply a voltage, a variable voltage, and I measure the resulting current as a function of that voltage, and then I plot it, as we just did in that previous example. So we have something here, it could be a complex circuit. We apply a variable voltage, Vx, measure the current, and then plot the current as a function of the voltage. So Ix as a function of Vx. And it could be all sorts of things, we don't know. That is what we call the IV characteristic of this black box. Okay, the other type of characteristic that we are also interested in is called input-output characteristic. And this one is a little different. We have a black box, and this black box has an input and an output. For example, it has an input voltage, which we apply from outside, Vx or Vin. And then there are some two terminals somewhere whose voltage difference we would like to measure. So this is what we would call Vout. And again, we would like to construct something like this. Vout as a function of Vin. What does it look like? So again, it could be some behavior, and that is called the input-output characteristic. If this circuit is linear, then this line is also straight, and preferably it goes through the origin. If the system is nonlinear, then all sorts of things can happen. And we will see in diode circuits that we get all sorts of nonlinear characteristics, either for that or for this. And that's very interesting. So this is just to show you what we are generally looking for when we analyze these types of circuits. This and or this. Okay, so now that we have that, let's go ahead and look at some more examples. So let's look at this example. We would like to plot the here's a circuit. We still keep the diode at the ideal, according to the ideal model, and we have a resistor here, we have a voltage, and we would like to plot two parameters here. Number one, Ix as a function of Vx, so that's an IV characteristic, and number two, this voltage V out as a function of Vx. So I will give you 90 seconds to think about this example. This is our quiz today. All right, I hope you managed to find the current and the voltage as a function of Vx. So let's go through this and see. As usual, if you are interested in Ix as a function of Vx, we assume that Vx is very negative and see what we can predict. So if Vx is very negative, what could happen? Well, it means that we're trying to make this point more negative than this point. We're trying to make the cathode of the diode more negative than its anode, so the diode will turn on. It's an ideal diode. So if the diode turns on, I have to replace it by a short circuit. So as long as Vx is negative, my conjecture is that this is what we have. We have a short circuit for the diode, and then we have a voltage source, Vx, and then we have R1, and this is Ix. So how much is Ix? Well, Ohm's law, Ix is simply Vx over R1. So it's just a plot like so, with a slope of 1 over R1. All right, now what happens if Vx crosses 0 and becomes positive? Well, if Vx is positive, we're thinking that it will want to create a positive voltage on this side with respect to this side. And as soon as the cathode becomes more positive, the diode turns off. If the diode turns off, we replace it by an open circuit. So over here, our equivalent circuit will be like this. It's an open circuit. It has no current in it. So the current will be 0. That was simple. You see that this behavior is complementary or similar to what we saw previously when the diode was the other way around. So by flipping this diode downward, I managed to flip this characteristic also this way. We used to have 0 current here and a proportional current on this side. By flipping the diode, we have a proportional current here and then 0 current on this side. Okay, in the next step, we need to plot V out as a function of Vx. And that is not that difficult either, given what we've seen in previous examples. So here's V out, and here's Vx. So again, when Vx is negative, the circuit reduces the structure. So let me redraw, just so that we can keep track of everything. The diode is a short circuit. And where is V out? V out is denoted as the voltage across the diode. So this is V out here. And this V out, we see, that is equal to 0. Because that is the definition of a short circuit. A short circuit can have any current through it, but the voltage is always 0. Ohm's law. The resistance is 0. So V out is 0 in this regime here. Okay, now what happens when Vx becomes positive? When Vx is positive, the diode has turned off because this side wants to become more positive than this side. The diode has turned off, we have this situation. This is V out. The diode is not there. I'll just draw an open switch here, but it doesn't matter. And then we have Vx. How much is V out in this case? All right, so this is what I talked about last time. You have to remember that the current through R1 is 0. R1 has no current because there's no path for the current to flow. If the current through R1 is 0, the voltage drop across R1 is 0. That means that this voltage is equal to this voltage. That means that this voltage is equal to this voltage. So V out is equal to Vx, regardless of the value of R1. So V out is simply equal to Vx, and that gives us a 45-degree line, so with a slope of 1. So this is also an example of a rectifier. If the voltage is negative, we stop it. If the voltage is positive, we let it go through. Okay, so that's an example of playing with circuits like this. Let me go through one more example in the remainder of the time that we have today. So let's go over here. We are still staying with the ideal diode model, just again to get comfortable with these concepts. We have plenty of time to later go look at the constant voltage model, etc. So in this example, let's try to connect our voltage, our variable voltage Vx, to a resistor like this, a diode like this, and then another resistor like this. So R1, R2. In fact, one interesting exercise that I can pose to you is take two resistors of unequal values and one diode and see how many different ways you can connect these together. And then for each of those connections, each of those topologies, try to perform this type of exercise. Apply voltage, measure the current, measure the voltage anywhere you want, plot these. That's a very good exercise to build up understanding and skill towards analyzing these circuits efficiently. All right, so in this circuit, our objective is to find Ix first. But there are many other interesting things that we would like to find. So let's start with Ix, and then we'll work our way. Again, Vx goes from minus infinity to plus infinity. All right, so let's draw the plane for Ix versus Vx. And we say when Vx is very negative, we are guessing that the diode will be off. If the diode is off, we draw the circuit to make sure we don't lose track of things. So in this regime here, where Vx is negative, we have Vx, then we have resistor R1, then we have an open circuit, then we have resistor R2. So how much is Ix in this case? Well, we see that Ix cannot flow anywhere. There's an open circuit here. So Ix is 0. So long as Vx is negative, Ix is 0. So that wasn't too bad. Okay, now, when Vx passes 0 and becomes positive, the diode will turn on, just like before. When the diode turns on, we replace it by a short circuit, again from the ideal diode model. So in this regime here, we have this, we have R1, and then we have a short circuit, which I draw as a switch again, and R2. So, and that is Vx. How much is Ix in this case? Well, we see that Vx sees two resistors in series. So Ix is equal to Vx over R1 plus R2. So in this case, Ix is 0. In this case, Ix is Vx over R1 plus R2. All right, so that's good. We just draw it like this, and this slope happens to be 1 over R1 plus R2. Okay, so that wasn't that bad. Now, in the next step, we'll be looking at some other quantities inside the circuit. Ix is one of them. In fact, there's only one current in the circuit because there's only one loop in the circuit. But there are other voltages that might be interesting. We have a voltage across R2, a voltage across the diode, and a voltage across R1. So each of those voltages is an interesting quantity. So we would like to plot each of these voltages as a function of Vx, as Vx goes from minus infinity to plus infinity. All right, so let's consider the voltage across R2 and see how that goes. So no problem. Again, we draw our plane. We will call this VR2. VR2 will be this voltage, VR2, as a function of Vx. Now the analysis that we did originally will help us here because we determined what the circuit looks like when Vx is negative or positive, and these results will help us in constructing this characteristic as well. Okay, when Vx is negative, we see that there is no current in the circuit because there's an open circuit here. Therefore, R2 has no current, which means it has no voltage drop across it from Ohm's law. That means that this voltage is 0. So long as Vx is negative and Ix is 0, VR2 is also 0. Okay. Now, what happens when Vx becomes positive? When Vx is positive, we remember that the topology reduced to this circuit on the right. And I am interested in the voltage across R2. So let me redraw that here to analyze it quickly. So here's Vx, here's R1, here's R2, and I am interested in this voltage here, VR2. How much is that voltage? Well, remember the equation for a resistive divider from basic circuit theory. We know that VR2 is actually equal to the voltage that we applied across this resistive divider multiplied by this resistor divided by the sum of the two resistors. So we have Vx times R2 divided by R1 plus R2. So we see that the voltage across R2 is proportional to Vx with a slope less than 1, obviously, right? If the slope were 1, it means that all of Vx is going to the output. But because of this attenuation, we have a fraction of Vx going to the output. So the slope is less than 1, and it is equal to R2 over R1 plus R2. In other words, as far as Vx and VR2 are concerned, this system says if Vx is negative, VR2 is 0. We don't give out anything. If Vx is positive, we will attenuate it by a certain factor and produce it at the output, if the output is here. If we put everything else in a black box and we say this is the input, this is the output, that's what the system will do to the input signal. Okay, in the next step, let's try to find the voltage across the diode. So we will call this VD1. We'll call this VD1, and let me change the color of my pen to maybe brown. All right, so VD1 as a function of Vx. Okay, well, again, we go back to the fundamentals, what we analyzed originally. We said if Vx is negative, the circuit reduces to this topology. So let me redraw that topology here. Vx, R1, R2. Now this is a little tricky. I'm trying to find the voltage difference between this point and this point, because this is where the diode is located. So how much is this voltage difference as Vx changes? Okay, all right, well, no problem. We know that when Vx is negative, the current through this branch is 0, as we saw before. That means that R2 sustains no voltage. R1 sustains no voltage. R2 sustains no voltage. So the voltage difference from here to here is 0. The voltage difference from here to here is 0. So then how much is VD1? If we write a KVL, we can see minus Vx plus 0 plus VD1 plus 0 is equal to 0. So minus Vx plus 0 plus VD1 plus 0 is equal to 0. That means that VD1 is just Vx. So all of this voltage goes to the output because these two resistors have no voltage on them. So that means in this regime, VD1 and Vx are just equal. We have a slope of 1. Unfortunately, I drew this too close, so let me try to move my axis to the left a little. So we'll draw it like this. And this is the characteristic that we have when Vx is negative. And the slope is just 1 because the input voltage just goes right to the output, comes out right here. So if Vx is negative, all of Vx goes to the voltage across the diode because the diode is off and there's no current in the loop. All right, how about when Vx is positive? Well, we said that if Vx is positive, the diode is on and the circuit reduces to this. So if the diode has become a short circuit, how much is the voltage across the diode? A short circuit has only 0 volts on it, right? That's the definition of a short circuit. We cannot have any voltage across it. So the voltage across the diode will be 0. So this is VD1 as a function of Vx. Okay, very good. Well, is there any other quantity that we might try to find? Well, there's one more quantity, and that's the voltage across R1. So let's try to plot that one too, just to have more practice in understanding diode circuits. So VR1 as a function of Vx. So VR1 will be defined as positive here, negative here. That's arbitrary. You can define it the other way too, but I just pick it like that. So I would like to plot VR1 when Vx is very negative. When Vx is very negative, the circuit is like so, the diode is off. If the diode is off, R1 has no current. If R1 has no current, the voltage across R1 is 0. So voltage across R1 is 0 all the way to Vx equals 0. What happens when Vx becomes positive? When Vx becomes positive, the circuit reduces to this structure. And now we have, again, a resistive divider, except that the voltage is taken not across R2, but across R1. So we have to draw the circuit carefully. Here, R1 and R2. And we are interested in this voltage. And we are applying Vx. So how much is the voltage across R1? Well, in analogy with this equation, I can say it's equal to Vx times R1 over R1 plus R2. In the previous case, we were interested in the voltage across R2. Now we are interested in the voltage across R1. If you don't like that, you can say that the current flowing through this branch is given by this equation. That current multiplied by this resistor gives me the voltage. So that current multiplied by the resistor gives me R1 over R1 plus R2 times Vx. So in this regime, we have R1 over R1 plus R2 as the slope of the characteristic. And that is what we get if we try to plot VR1 as a function of Vx. So we see that the rectification property manifests itself in all of these plots in one form or another. Sometimes it passes negative values, sometimes it passes positive values depending on what we are interested in. And we also have certain slopes associated with these characteristics depending on the voltages that we're trying to produce. Okay, this was a quick example of a slightly complex circuit once we have two resistors and one diode. Now you can think of maybe one resistor and two diodes, or two resistors and two diodes, and become more efficient at solving these circuits. All right, I will see you in the next lecture.